Hi, I'm Paul Mirsky. I'm the guest producer for today's episode of Ace Physics, and I'm also the creator of Symmetry Optics. If you want to learn more, go to symmetryoptics.com.
Here's an outline for today's video titled The Physics of How LCD Screens Manipulate Light and the Jones Vectors That Describe Polarization. In the previous video in this series, we discussed ordinary LCD projectors and holographic projectors. This is a thumbnail to the video titled LCD Projectors, Holography, and Fourier Optics. The link is in the description. In this video, we'll explore the fascinating physics behind LCD screens and how they manipulate light. We'll start with some powerful mathematics, Jones vectors, a precise way to represent polarization of light. Don't worry, the math will be accompanied by a clear animation to make it intuitive. Then we'll move on to a series of fantastic demonstrations, revealing how LCD screens rotate polarization to manipulate phase and how spatial light modulators work. This lesson will not only deepen your understanding of polarization, but also showcase the incredible engineering behind modern display technology. So stick around, there's a lot to see. And here's an outline of the talk. The mathematics behind LCD screens, the Jones vectors, several exciting demonstrations, including how LCD screens rotate polarization to create images, revealing text using polarization instead of brightness, seeing an image form in real time, pure physics magic, the physics behind how LCD screens control light by rotating polarization and modulating phase. In a previous video, we explained Stokes vectors, which describe both fully and partially polarized light. The link to the video is in the description. Here's a picture of the thumbnail. This video will focus on Jones vectors, which are used for coherent light like lasers. Unlike Stokes vectors, which have 4 dimensions, Jones vectors are 2-dimensional and only apply to fully polarized light. The Jones vector shown here represents horizontal polarization. In the following slides, I will provide a detailed explanation of Jones vectors, their mathematical properties, and their role in modeling light modulation. Next, Paul Mirsky will demonstrate the function of a spatial light modulator and explain how an LCD screen manipulates light polarization using Jones vectors as the eigenstates of the LCD screen for precise mathematical representation.
Imagine a collimated laser beam traveling in the z direction. The xy plane is perpendicular to the beam. If we look at a cross-section of the xy plane, we see an electric field. One way to visualize the field is a bunch of little arrows all over the plane, all pointing in the same direction, although they usually have different strengths. A Jones vector describes the direction of this electric field. It has 2 dimensions, which represent the horizontal component and the vertical component. In this example, the arrows point anti-diagonally, so the horizontal component is 0.707 and the vertical component is minus 0.707. The Jones vector is always normalized to length 1, and the number 0.707 is a shorthand for root 2 over 2, and this is the magnitude when the horizontal and vertical components have equal strength.
Jones vectors describe the polarization state of light. For horizontally polarized light, the electric field oscillates entirely in the horizontal direction. This is its Jones vector, given by 1, 0, meaning it has a horizontal component of 1 and no vertical component. For vertically polarized light, the electric field oscillates along the vertical direction, with a Jones vector of 0, 1, indicating no horizontal component. The entries of the Jones vectors are complex numbers, but only the real part corresponds to the observable electric field. I'll illustrate this shortly with an animation. After all, if a picture is worth 1,000 words, an animation is worth 100 pictures. This slide contains the 6 major polarization states of light. The first 4, horizontal, vertical, diagonal, anti-diagonal, are linearly polarized states, where the electric field oscillates in a straight line. These 2, which are eigenstates of the LCD screen, are right and left circularly polarized light, where the electric field rotates as the wave propagates. In this animation, we'll visualize different polarization states of light using the Jones vector. We'll start with horizontal polarization, move to diagonal, and end with right circular polarization. Here is the Jones vector 1, 0. In complex notation, it's 1 plus 0i and 0 plus 0i, meaning the electric field oscillates purely along the x-axis with no vertical component. The 2 graphs on the left represent the Jones vector multiplied by a time-dependent complex exponential. The top graph represents the horizontal component, while the bottom graph represents the vertical component, which remains 0 for horizontally polarized light. The right graph shows the actual polarization of the light. As the complex number rotates, the projection on the x-axis determines the horizontal polarization. Since the vertical component is 0, the light oscillates back and forth along a straight horizontal line. This graph represents the actual polarization of the light. The electric field is oscillating back and forth along the x-axis. As this complex number rotates, the projection onto the x-axis represents the horizontal polarization. For example, this is projected at about -0.8, and as you can see here, the electric field here has a magnitude of about -0.8. Right now, the projection is roughly 0, and at this time, the electric field is 0. The electric field oscillates back and forth as the projection of this complex number. This Jones vector, 0.707, represents diagonally polarized light. Now, both horizontal and vertical components of the Jones vector are present and oscillate in phase. At time t equals 0, the projection onto the horizontal axis is 0.707, and the projection onto the vertical axis is 0.707. The electric field vector is 0.707 in the horizontal direction and 0.707 in the vertical direction. Since both oscillate together, the projections combine to form a diagonal oscillation. The right graph visualizes the resulting polarization. The electric field moves back and forth along a 45-degree line. This represents linearly polarized light oriented diagonally. The Jones vector 0.707 and -0.707i represents right circularly polarized light. At the beginning of the cycle, the horizontal component of the electric field is 0.707. At this time, the vertical component of the electric field is all imaginary, meaning the electric field at that time is 0. For right circularly polarized light, the two components of the Jones vector are out of phase by 90 degrees. The vertical component lags behind the horizontal component by a quarter cycle. You can see this in the graph on the left. The phase difference results in a continuous rotation of the electric field. The projections on the axes determine the horizontal and vertical components of polarization. On the right, we see that instead of oscillating along a straight line, the polarization traces a circular path as the light propagates, demonstrating that the electric field rotates in a right-handed circular motion. And here's the vector for left-handed circularly polarized light.
Next, we'll consider optical devices which act on the polarization. This device is a liquid crystal array. It contains two sheets of glass, and sandwiched in between them is a very thin layer of liquid crystal. Under a microscope, you can see that it's divided into roughly 1 million pixels, although you might be seeing some weird artifacts depending on your screen. This thing is a marvel of engineering. Each pixel can be energized individually, but for now, we're going to energize them all together as though they were a single giant pixel. Here's how the liquid crystal works inside an LCD projector. We start with a vertically polarized source, which is shining on this target. If we pass the vertical source into a horizontal polarizing filter, the light gets absorbed and we see a dark spot on the target. If we place the liquid crystal before the horizontal filter, but we energize the crystal, then it has no effect. The light stays vertical and it still all gets absorbed at the horizontal filter. The target stays dark. If we do not energize the crystal, the light gets rotated from vertical to horizontal, and it passes right through the horizontal filter. This gives us a bright pixel. If the liquid crystal is partially energized, the light gets partially rotated, gets partially absorbed, and partially passes through the horizontal filter. This gives us a gray pixel.
Light polarization can be described mathematically using vectors and matrices. In this demonstration, we'll see how a liquid crystal device modifies the polarization of light and how these transformations can be represented using matrix multiplication. We begin with vertically polarized light incident on a liquid crystal that is energized. Because the crystal is energized, it does not change the polarization state of the light. Mathematically, this is represented by multiplying the Jones vector for vertically polarized light by the identity matrix. Since the matrix leaves the vector unchanged, the output remains vertically polarized. When this light passes through a horizontal polarizer, it is completely blocked, resulting in a dark spot. Vertical light cannot pass through a horizontal filter. When vertically polarized light is incident on a completely unenergized liquid crystal, it's rotated to horizontally polarized light. This is represented mathematically by multiplying the vertically polarized Jones vector by the so-called sigma y Pauli matrix. This produces a Jones vector representing horizontal polarization. The horizontal light passes through the horizontal polarizer and leaves a bright spot. When vertically polarized light is incident on a partially energized liquid crystal, it produces a diagonally polarized output. This can be represented mathematically by multiplying the vertical polarization Jones vector by the so-called handmade rotation matrix to produce a diagonal polarization. The diagonally polarized light incident on a horizontal polarizer is only partially transmitted, leaving a gray spot, where a gray spot is not as dark as a dark spot, but not as bright as a bright spot. Linearly polarized light is the input for an LCD projector. Circularly polarized light is the input for a holographic projector. Circularly polarized light is an eigenstate of a non-energized liquid crystal. There will be an animation later in the video to help you understand this, along with a fantastic demonstration of how a holographic projector forms an image as the light propagates through space. For now, let's move on to the demonstrations of how LCD screens work by selectively rotating polarization at different pixels to create an image.
There are about 1 million pixels in this array, and up to now, we've been energizing them all together as if they were one giant pixel. But actually, we can energize them individually. And in order to be able to see that, we're going to use my homemade imaging polarimeter. I named it Monet after the painter, because it reminds me a little bit of water lilies in a pond. Briefly, it's a camera that takes a whole set of images through different polarizing filters. Then it combines those different images mathematically to figure out the polarization at each location, and it displays a polarization image using false colors. To see an example, we'll point Monet at the liquid crystal, and I'll put some text up on the array, which is very easy because my computer just thinks that it's a monitor. We'll gather a data set and compute the polarization image. Here it is. This picture shows text in yellow on a blue background. It's not actual yellow and blue light. In terms of actual color, it's all red laser. But the way the Monet app is configured right now, the blue indicates vertical polarization and the yellow indicates horizontal. You can see a little bit of green, and depending on the exact shade of green, it's somewhere in between vertical and horizontal. The input is blue. In all the pixels that make up the text, the crystal is rotating the light to horizontal. At the current stage, blue and yellow are still the same brightness. We can see this directly if we pass the light through a lens and form an image of the liquid crystal array onto a thin piece of white paper which is partly translucent. It's not a very useful projector because the different polarizations light up the paper exactly the same, and our eyes can only see brightness differences. So, we place a horizontal filter in the path, and now we can read it. It's still not a very useful projector because it's only 1 inch tall, but it's progress. In principle, this is working like an ordinary LCD projector, which is the first of our 2 projector types. Next, we're going to gradually introduce the second projector type, the holographic projector.
Next, we will be using right circular and left circular polarized light instead of horizontal and vertical polarized light. Previously, yellow represented horizontally polarized light and blue represented vertically polarized light. Now, with circular polarization, yellow represents right circularly polarized light and blue represents left circularly polarized light. When right circularly polarized light is incident on a fully charged liquid crystal, it remains in a right circular polarized state but acquires a phase shift. This means that after passing through the energized liquid crystal, its position along the circular path shifts. This is the right circularly polarized light before entering the fully energized liquid crystal. This is the right circularly polarized light after leaving the fully energized liquid crystal. It's still right circularly polarized, but it has a phase shift, meaning it's moved to a different location along the circular path. Similarly, when left circularly polarized light is incident on a fully energized liquid crystal, it stays in a left circular polarization state, but also gains a phase shift. This causes it to jump to a different point along its circular path after passing through the energized liquid crystal.
Right now the light is vertical, but we are passing it through a quarter wave plate. And as I rotate this quarter wave plate, it's going to change the polarization from vertical to elliptical to right circular, and then to horizontal, left circular, and then back to vertical. I'll change the input to be right circular. That's an eigenstate of the crystal. We'll collect the data, and here's our polarization image. Now, yellow's indicating right circular, and the entire field is yellow. You can just barely make out some letters. The crystal is having almost no effect on the eigenstate, which is just what we expect. Switch now to a left circular input, the other eigenstate. Collect. And it's the same thing. The whole field appears blue, indicating that it's all left circular. In other words, no change from the input. But what Monet does not show us is that the phase of the text is different from the phase of the background. Phase is fundamentally invisible to this camera. We can only notice the phase by its effect in another plane far away after the light has diffracted and interfered to produce a far-field pattern. To make it a holographic projector, we need to change the pixel pattern to this holographic mask. We showed this odd-looking pattern already in the previous video on the holographic projector. Check the link in the description. The mask looks messy and random, but it's actually anything but random. If you take the Fourier transform of this pattern, it rearranges the information which is encoded in all the fine details, and voila! A beautiful image appears. The Fourier transform is a mathematical procedure which can convert one bitmap into another. But amazingly, a pattern of coherent light actually undergoes the Fourier transform gradually as the light propagates through space. I always find it remarkable how a physical action like wave propagation can be an exact manifestation of a completely abstract mathematical concept like the Fourier transform. To operate the holographic projector, we start with a bitmap of the image we want to project. We compute the inverse Fourier transform to produce the mask. We put the mask on the liquid crystal array and pass the laser through it, which imprints a pattern of phase shifts over the wavefront. The brighter a pixel looks in this rendering of the mask, the more the phase gets shifted at that point. The laser propagates and undergoes the forward Fourier transform, which gets us back to our pattern, which is now projected onto a wall far away. We'll try it out by displaying this mask pattern on the liquid crystal array. First, we'll give it a vertical input, which is the wrong input, just so that you can see the pattern. Different pixels are energized to different degrees, so the pixels are yellow, green, and blue. Next, we'll change the input to right circular, which is an eigenstate. Looking at the image, the mask does not seem to be changing the polarization. But even though we can't see it, the phase has shifted by various amounts in various pixels.
AcePhysics.org, Math and Physics Tutoring with Dr. Hudis.
To see the effect in the far field, we take the polarimeter out of the way and let the light propagate towards that wall, which is about 15 feet away. To show you the details of this pattern, I'm going to hold my phone camera right up to this target so that it's recording the spots, and then I'm going to start walking away from the laser. Right now, I'm about 1.5 feet away. And now I'm about 5 feet away and things are starting to look like something. Maybe 8 feet or so. 10 feet. And now we are at the wall. And here's our projected image. Remember though, that the holographic projector only works when the input is right circular.
Now let's address the question of how the liquid crystal rotates the polarization of light. This diagram shows a single liquid crystal pixel. At the top and bottom are polarizing filters, P1 and P2, with transparent glass electrodes right beneath them. The inner surface of the glass electrodes are coated with rubbed alignment layers that control the orientation of the liquid crystal molecules touching the glass electrodes. Between the electrodes is a layer of polar rod-shaped liquid crystal molecules, which twist smoothly from bottom to top when no electric field is applied. These molecules align with the direction of the rubbed coating on each electrode through weak dipole interactions. The yellow arrow represents light passing through the pixel. This is the unenergized state, when no voltage is applied across the liquid crystal cell. The liquid crystal molecules naturally twist in a helical shape, turning the light's polarization by 90 degrees as it passes through. Light enters the display and is first polarized by the bottom polarizer, P2. As it travels through the twisted liquid crystal layer, its polarization rotates by 90 degrees. The rotated light can now pass through the top polarizer because it matches the orientation. The polarizer P1 is rotated 90 degrees relative to P2. As a result, the pixel appears transparent and lets light through. This is why the display appears bright in the off, non-energized state. Light is not blocked. There's a voltage source that can be switched on or off between the two glass electrodes. In the off state, when no voltage is applied, the liquid crystal molecules naturally twist into a spiral because they are weakly attracted, mainly through dipole interactions, to the alignment layers of the electrodes. These electrodes are specially treated by rubbing or coating them with a material that causes the molecules to line up in a specific direction, matching the orientation of the adjacent polarizer. The alignment layers force the molecules at the top and bottom to point in different directions, so the entire layer twists gradually by 90 degrees from one surface to the other. You can think of it like water flowing through a gentle, curving stream. Just as the water smoothly follows the bends of the stream, the light's polarization follows the twists of the liquid crystal molecules. As a result, the polarization of the light rotates by 90 degrees and matches the orientation of the top polarizer, allowing it to pass through and making the pixel appear bright and transparent. In the on or fully energized state, applying voltage across the electrodes creates an electric field strong enough to override the weak dipole forces that normally twist the liquid crystal molecules. Although the electrodes are treated with rubbed alignment layers that guide the molecules into a twisted shape, the field forces them to align straight along its direction. Without the twist, the light's polarization is no longer rotated, so when it reaches the top polarizer, it's in the wrong orientation and gets blocked by the polarizer filter. As a result, the pixel appears dark or opaque. When the liquid crystal molecules are twisted, they gradually rotate the light's polarization as it travels through, because their orientation changes along the path. But when the molecules are aligned straight by the electric field, there's no variation in direction, so the light polarization stays the same. The straight molecules act like a passive medium, not twisting the light as it travels. As a result, the light reaches the top polarizer in the same orientation it entered.
Birefringence is a different way to change the polarization state of light than using liquid crystals. Birefringent materials have two distinct refractive indices depending on the polarization direction of incoming light. As light passes through, its polarization components travel at different speeds, creating a phase shift that changes the light's overall polarization state. This provides a passive, material-based method for manipulating polarization, distinct from the electrically controlled molecular alignment used in liquid crystals.
The maximum effect on polarization occurs when there's a relative phase shift of -1. In other words, halfway around the unit circle. This little plastic card is a lot simpler and a lot cheaper than the liquid crystal, but it's still special because it's birefringent. That means that it has one index of refraction in the fast axis, which is the vertical direction, and a different index of refraction in the slow axis, which is horizontal. And if we just hold it at 45 degrees, it's still birefringent, but now the fast and slow axes are diagonal and anti-diagonal. Now we're seeing vertical light, which gets absorbed at the horizontal filter, and the output is dark. If we place the card in the beam with the fast axis vertical, the light is an eigenstate of the card, and so there's no effect on the output. It remains dark. But if the card is at any other angle, the light is not an eigenstate of the card, so the polarization changes and some of the light comes through the horizontal filter.
AcePhysics.org, Math and Physics Tutoring with Dr. Hudis.